Vanakkam. Welcome to this course on classics in neuroscience. In this series of videos, we have been looking at the physiology of the synaptic potential and the receptor potentials. In this video, we will look at the crucial contribution of Bernard Katz in his description and in helping us improve our understanding of the end plate potential and synaptic quanta. So, in 1948, Paul Fatt, an American scientist, joined Bernard Katz, and they initiated their intracellular study of synaptic transmission in frogs neuromuscular junction. They started this work in 1948. So, Paul Fatt is a forgotten hero, is an excellent experimentalist, is a brilliant experimentalist who is famous at least on two counts. First, for his collaboration with Katz to describe the end plate potential in a muscle, and his collaboration with Eccles to describe the nature of synaptic inhibition, which happened later. In his work with Bernard Katz, Paul Fatt helped identify the end plate potential, which is the response that the muscle cell produces as the neuron is stimulated. As the presynaptic neuron is stimulated, the response produced by the muscle is the end plate potential that then leads to action potential. The initial response produced by the muscle is called as the end plate potential. This was described by Fatt and Katz in 1951. Of course, this was supported by other people and other works that we have discussed previously. For example, the work of Rene Cotier, George Coyle, who worked using other methods. But here they used microelectrode based recordings to establish this. This is more direct evidence of the presence of acetylcholine, for example, as a neurotransmitter. So, the presence of acetylcholine as a neurotransmitter was established using this method now. This end plate potential as a means to, as a physiological mechanism of synaptic transmission was crucial, was the crucial first step in improving our understanding of synaptic communication. This continues to be a leading model system, a leading example. Even today, this is a very important model system. In the meanwhile, there were other model systems that were being used. For example, the model of squid giant axon. Of course, that is a totally different topic that we have discussed in the previous set of videos. While Fatt and Katz were recording EPPs at high gains, EPPs means end plate potentials at high gains, they found that there were very small all or nothing responses that then summed to give the full EPP. These really small unitary responses, these really small quanta of responses came to be called as the miniature end plate potential. Katz spoke about this in later talks. He used to check every time when he found one small quanta getting released, he used to check maybe it was AV's heavy footsteps on the corridor that is causing this, as a joke. Maybe that is what is causing this noise, is what he thought. But later it was realized that this is maybe because of individual vesicles releasing their entire quantum of neurotransmitters. Many of these individual vesicles simultaneously release all of their neurotransmitters to lead to the final summed end plate potential. But when one vesicle releases its neurotransmitters, that is called as the smallest functional unit of action, or the miniature end plate potential, that end plate potential that would be produced by one vesicle, not one molecule of acetylcholine in this case, because we are studying neuromuscular junction, the neurotransmitter is acetylcholine. This is not the amount of potential change that would be reflected in the postsynaptic cell due to one molecule of acetylcholine, but rather the change in the end plate potential that happens, or the end plate potential that happens due to one vesicle. Remember, one vesicle can contain 1000 molecules or thousands of molecules of acetylcholine. This is the smallest unitary change. That is, when this vesicle is releasing, it is not like it will take back half of its quantum of acetylcholine. When it releases the whole quantum of acetylcholine. This is the smallest amount of acetylcholine that can be released. It is not possible for the presynaptic cell to release acetylcholine at the rate of one molecule per release. That is not possible. It can release at the rate of one vesicle per release, and one vesicle contains thousands of molecules of acetylcholine. So, the end plate potential that is realized due to the release of one vesicle is called as miniature end plate potential. So, as you have seen from our discussion of neuromuscular junction and the videos from the neuroscience of human movement course, you would have seen how the neuromuscular junction functions. See, this is an all or nothing response, and also this is a mandatory response. So, whenever you have an action potential in the presynaptic neuron, the muscle cell always fires. The muscle cell always produces an action potential. It's an obligatory synapse in that sense, one of the very few obligatory synapses. So, when an action potential arrives at the presynaptic terminal, it is not going to release just one vesicle, it is going to release a whole bunch of vesicles. It is going to release a large number of vesicles, each containing the same, approximately the same number of molecules of acetylcholine. So, if for example, there are n vesicles that are released and each of them is containing m molecules of ACH. For example, the number of molecules of acetylcholine that attaches to the postsynaptic cell will be n times m. Remember, this is going to be always a multiple of m. For example, in a different case n minus 1 in a different muscle, or in a different case n minus 1 might be released, or n minus x number of vesicles might be released, but it will still be a multiple of n minus x times m. So, which means that the smallest amount of acetylcholine molecules that can be released is actually 1 m, is just m, that is when one vesicle opens. So, when n vesicles are released and each of them contains m molecules, so you are going to have n times m number of molecules of acetylcholine getting released into the synaptic cleft. So, all of these actions together sum to produce the final end plate potential. Right. So, this is the connection between the amplitudes of quanta, their numbers, and this work was done by Del Castillo and Katz 1954. So, where they describe, I am going to read from the original text. Suppose we have at each nerve muscle junction a population of n units capable of responding to a nerve impulse. Suppose further that the average probability of responding is p. So, probability of responding is p. There are n units, number of vesicles is n. Okay. Then the mean number of units responding to one impulse, what is going to be that mean? That mean, let us say that mean m1 is np, is it not? The probability of response of each times the number of units that are available. So, a classic statistical approach, where p is very small, the number of units of x that make up the end plate potential in a large series of observations should be distributed in the characteristic manner of the Poisson's law. Right. Check that out. So, these questions essentially what do? They relate the amplitude of the quanta, their numbers and the probability of synaptic transmission. Remember the frequency of the EPP or frequency of the miniature EPP is controlled or determined by what happens at the presynaptic terminal. The amplitude of the response is controlled by what happens at the post-synaptic terminal. So, how frequently you are going to have action potentials in the postsynaptic neuron is something that is determined by what happens in the presynaptic terminal. But what is going to be the amplitude of the postsynaptic muscle cell in this case, not the neuron, is determined by what is the setup, what is the situation in the postsynaptic terminal. So, this formulation became the fundamental formulation in improving our understanding of synaptic transmission, just like how the Hodgkin and Huxley description became the fundamental formulation to describe action potentials. So, this was the idea. Also, it was realized that membrane potential played a crucial role in the control of miniature potentials. So, membrane potential. Also, in collaboration with Milady, Katz described a crucial role of calcium. If you had watched my previous video on this subject, you will realize that the amount of calcium that enters inside the presynaptic neuron depends on the resting membrane potential, the difference between the resting membrane potential and the action potential. So, as more and more calcium enters inside, it is sensed by a calcium sensor that then causes the SNAR proteins to, or the vesicles and the SNAR proteins to release the neurotransmitter, is what we have seen. So, the crucial role of calcium was described by Milady and Katz in 1963. Additional studies by Lilly showed that the release probability was perhaps controlled by membrane potential. Okay. As soon as this data by Del Castillo and Katz was published, it was immediately realized that what the electron microscopists were seeing in their electron microscope, the vesicles, were the vesicles that were identified by Bernard Katz. So, also clearly one vesicle contains thousands of acetylcholine molecules, and many of these vesicles simultaneously open on the other side of the plasma membrane. This process is called as, of course, this process is called as exocytosis. So, this was recognized, this nature of this physiological quanta and their rather unexpected nature was recognized. Of course, this was correlated with electron microscopy, and how much of acetylcholine is getting released is a function of both of this. The region where the vesicles fuse onto the plasma membrane and releases the neurotransmitter came to be called as active zone. Okay. This came to be called as active zone. So, MEPP, that is miniature end plate potential, miniature EPP, that is found when one vesicle releases its neurotransmitter, is the fundamental unit of action. So, this is similar to the description of the atom in physics, or the description of the chemical bond in chemistry. Likewise, you have the miniature end plate potential in neurophysiology. Of course, later with the help of newer technologies, it was possible to study this better, and also each step in the release of this neurotransmitter can go wrong, and they do go wrong and cause some diseases. All of this I have described in a previous set of videos in the previous course, which is that that video is called as diseases of the neuromuscular junction, or the toxins that could cause damage or that could limit the function of neuromuscular junction. Please do check that video. With this, we come to the end of this video. In this video, we looked at end plate potential, synaptic quanta, the miniature end plate potential, which is the smallest functional unit of neurophysiology, like chemical bond is to chemistry, like atom is to physics. Yes. Thank you very much for your attention.